Professor Bialis here. In this video we're going to be talking about section 11.4, which is nonlinear inequalities. So what we're going to be doing is essentially taking a two-dimensional problem and only looking at it in a one-dimensional space. Okay, so let me show an example, and then I'll show you what I mean by the two-dimensional, one-dimensional thing. The process we're going to be going through today is very, very basic. It's just lengthy. There's going to be a lot of arithmetic behind it, a lot of work behind it. So just be patient, be organized in your work, and beyond that, it's very, very straightforward. But as always, try to make this a routine. That's all this is. We're trying to learn these tools so that when we get into a calculus or a stats or some other application class that is specific to our major, then we have these tools at the ready so we can use them to solve problems that are given to us. Okay, so first one, let's look at, I simply want you to solve x minus 2 times x plus 4 is greater than 0. Let's look at that. Okay, so as you can see, we have an inequality. This, if we distributed that out, we would have a quadratic, so it's not linear, okay? So that means we can't just isolate the x and be done with it. So what we're going to do is first, whenever we have something like this, a polynomial of any kind on this side, we want to have a 0 on the other side, which we already have, and then we're going to solve this like as if this was an equation, okay? So if we have the 0 on one side, we're just going to set each of those factors equal to 0. So x minus 2 equals 0, x plus 4 equals 0. Add the 2, subtract the 4. And we have those, okay? Now, the reason we're doing that is because 0 is kind of a checkpoint along the way. We want to know when we're bigger than 0. Well, when we're not bigger than 0, we would be at 0 or below it. Okay, so that 0 is kind of a midpoint or a checkpoint that we need to identify. And then we can decide which side are we going to be on. Okay, when are we going to be bigger, when are we going to be smaller? So what we're going to do is take these values here and place them on a number line. Okay, so we have a -4, we have a 2. Now I said we're going to take a two-dimensional problem and look at it in one-dimensional space. This is a one-dimensional space. A two-dimensional space would be when we have that Cartesian plane, which is the x and y axis. Now this number line we're creating right here, that's your x-axis, okay? If we look at these values, the -4 and the 2, what we're finding here essentially are the y-intercepts of the graph, I'm sorry, the x-intercepts of the graph of this. So we have these 2 points, like so, okay? Now if we were to graph this with that x squared, we would get that U shape of a graph. So we would have something like this. Okay, so there's your two-dimensional problem. Where is the graph bigger than 0? Okay, but we're looking at it only on this one-dimensional x-axis. Okay, when we get more experience and more knowledge of the graphing, then we can just go to the two-dimensional space and bing, bang, boom, get our answer. But until we get there, we're going to just look at this one-dimensional space. Now, how do we use this to analyze this? When we create a number line with those key points on it, we just broke that number line into 3 different regions. Okay, I'm going to call it region A, B, C. What we're going to then do is test to see where there are values that are here, here, or here. So I'm going to create a table with 3 different rows. And then I'm going to pick up test points. Now the test points are simply numbers that fall within these regions. So let's say -5. Let's say 0, that's always a good one. And let's say 3. You can pick other values if you want, just pick something that falls within there. And then what I do is I plug them into here and see if it's true or not. So if I go with this negative 5, I have negative 5 times negative 2, or I'm sorry, negative 5 minus 2, and negative 5 plus 4. I want to see if that's bigger than 0. Same thing here. Okay, let's work this out. Negative 5 minus 2 is negative 7. Negative 5 plus 4 is negative 1. Negative 7 minus 1 is 7. Is 7 bigger than 0? Yes, that is true. 0 minus 2 is negative 2. 0 plus 4 is 4. Negative 2 times 4 is negative 8. Is that bigger than 0? No, that is false. And here, 3 minus 2 is 1. 3 plus 4 is 7. 1 times 7 is 7. Is 7 bigger than 0? Yes. Okay? So what I found was that this region was true, and this region was true. So my final answer is negative infinity to negative 4, and 2 to infinity. Always parentheses here, and since we're not looking for equal to, we have parentheses here. And that's it. Okay? Now, look at that in the two-dimensional space. In that two-dimensional space, we are trying to see where that graph is bigger than 0. Bigger than 0 simply means above the x-axis. Well, that was true here and here. Negative infinity to negative 4, 2 to infinity. That's why I said when we get to graphing this easily, then this is going to be a lot less work than doing all this calculation. But until then, we got to do the calculation. Okay? And the other good thing about this is this can be used for any kind of graph. Okay? Quadratics are not that difficult to graph once you figure out how to. But if we get into rationals or just polynomial functions in general, graphing is always going to be more work than doing this. Okay? So that's pretty much it. Just make sure you solve this, using normal methods, create your regions, and then test them out. Let's look at a few more examples. Let's say we have this. Now, again, we have a quadratic, so it's not linear. We have that 0 on one side. We need to solve this as if it was equal to 0. So what I'm going to do is simply factor out a GCF of x. Whoops. We're here. And then I set each of those factors equal to 0. This is good. And then this, I have to add that 6, and we got that. Okay? Now, what I would then do is put those key values on the number line, and same as last time, I have 3 regions that I need to check. So I'm going to create a table, and pick 3 test points. I'm going to go with, let's say, negative 1, then 1, then 7. Okay? Again, pick whatever numbers you want as long as they're falling within those regions there. And then I plug it in. Now where you plug it in is up to you. You can plug in here or you can plug in here. If you're using the calculator, the less parentheses the better. Okay, so I would probably go here. But if you're doing this using mental math or by hand, I would probably go with this. Someone may say, well, that's not safe because what if you made a mistake with the factoring? If you made a mistake with the factoring, these are wrong anyways. Okay, you got bigger problems than that. So when you're checking at the very end of a problem, again, have to go to the original. But while you're still solving, use whatever spot in the problem you want. Again, if it's wrong, then you got to go back and fix it anyways. Okay, so let's go with this. I'm going to go with negative 1, then negative 1 minus 6. I want to see if that's less than or equal to 0. then 1, 1 minus 6, 7, 7 minus 6. We got that. So I have negative 1 times negative 7. I want to see if that's less than or equal to 0. That's a 7. So 7 less than or equal to 0, that is false. Over here I have 1 times negative 5. That's negative 5. Is that less than or equal to 0? Yes, that's true. And then over here I have 7 times 1, which is 7. Is that less than or equal to 0? No, that is false. So all I have working for me is this region in between. And since I'm looking for or equal to 0, I am going to be including these, so I have the interval 0 to 6. And there we go. Okay. If you notice on this one and the previous one, we alternated the trues and falses. The previous one we had true, false, true. Now we go false, true, false. If it's a quadratic, typically that happens, okay? However, please don't look, well, if this is false, then I'm just going to skip this and I'm going to go with these. Because if something's wrong in that first one, you're not going to see it, okay? Also, there are certain situations where if the quadratic, places itself in a certain way, or if we have a polynomial or a rational, we could break that alternating pattern, okay? So please don't rely on that to do the problem. Let's look at another one. So again, we got 0 on one side, which is a good start. Notice though, this is no longer a quadratic. We have a cubic function. If you distribute all that, you'd have an x cubed in the front. You do not treat this any differently. The only difference is we're going to have more key values and more intervals, okay? This is one of those situations though, where even when you know how to graph these polynomial and cubic and quartic and all that other stuff, when you know how to graph that, that's still going to probably be more work than just plugging into a table, okay? So we got the 0, and this is factored, which is excellent because then we can just set each of these equal to 0. Piece of cake, okay? So I'm going to add the 2. I'm going to subtract the 1. I'm going to subtract the 5. Okay? Put that on a number line. Make sure you write them in numerical order. So I go -5, -1, 2. And then I just plug and chug, okay? I'm going to create a table with 1, 2, 3, 4 rows. And then pick your key values. Pick nice numbers. I'm going to go with -6. I'm going to go with -2. Always use 0 if it's possible. And I'm going to go with 3. And then I just plug them in. I'm going to plug them into this original and see how that works out. Plug them all in. I like to do kind of one thing at a time so I'm focused on the same type of thing and I'm not bouncing back and forth. So I like to plug it all in, then I can focus on all that calculating. So I've got -2 minus 2, -2 plus 1. You kind of create an assembly line feel when you do it that way. And again, please don't think that I'm trying to avoid, deep thought or analyzing or anything. Right now we're just doing calculation, okay? So let's just go through it. Okay, Now, another thing to keep in mind, if the calculation, if the numbers start getting too big for you, here's something that we can remember. We're trying to see when this is less than or equal to 0. Okay, what does that mean? It has to be negative, right? It has to be negative or equal to 0. Do we need to calculate the exact value to figure that out? We don't. I'm not saying you shouldn't ever do that, okay, or it's bad to calculate. The number's fine, but all we care about really is the sign. So watch. Negative 6 minus 2, it's negative 8. But all I really care about is that it's negative. Negative 6 plus 1 is negative 5, but again, it's negative. Negative 6 plus 5 is negative 1. Now, if I have a negative, it's negative 8, negative 5, negative 1. But if I have negative times negative, it's positive times negative is negative. Okay? The fact that it's a negative 40 doesn't really matter. All I care about is that it's negative. Is a negative less than or equal to 0? Yes. So if the numbers kind of start scrambling your brain, just look at the signs. Okay? So what I then get here is a negative 4. Here I have a negative 1. And here I have a positive 3. Again, the numbers are pretty small. You get a 12, no big deal. But what we really care about is that this is positive. Is a positive less than or equal to 0? No. Here I got negative 2. I got a 1. I got a 5. It's a negative 10. Is negative less than or equal to 0? Yes. And then finally, I have a 1. I have a 4. I have an 8. What I really care about is that it's all positive. Less than or equal to 0, that is false. So what I get is true, false, true, false. So my intervals are negative infinity to negative 5, and then negative 1 to 2. And since it's or equal to, I have brackets everywhere except for that parenthesis, because that's always, except for the infinity, because that's always going to have a parenthesis. Tie that together with a union, and there's our answer. Okay? So, let's look at something a little different now. The first two were quadratic inequalities. This was a cubic, or you could just think of it as a polynomial inequality. Now let's look at some rationals. Okay. Now, with this, we have this rational expression here. We still want to have a 0 on one side, so that's a good thing to start with. Now, we're going to treat this almost like a polynomial. Polynomial, we set each of those factors equal to 0. In this case, we're going to set the numerator equal to 0 and the denominator equal to 0. So x minus 3 equals 0. X plus 5 equals 0. When we set the factors equal to 0 before, remember we were looking for those x-intercepts essentially. That's what this is giving me here. When this numerator is equal to 0, I'm finding those x-intercepts. Those are key x-axis points. When I set that denominator equal to 0, when did we do that in the past? We did that when we were looking for excluded values within the domain. So this is going to be a value that we want to exclude, or when you get into graphing rational functions later on, like a college algebra or a pre-calc class, you're going to look at those as vertical asymptotes. Those also are key values or key features along the x-axis. Don't worry about the asymptote idea, but I want you to understand why we're doing it like this. This is giving me a key feature on the x-axis. This is giving me a different key feature on the x-axis. Okay, so I'm going to solve these to get x equals 3 and x equals negative 5. Okay, same thing as before. Negative 5, 3. Okay, I have 3 regions. Create a table, 3 rows, and I'm going to pick negative 6, 0, and let's say 4. See what happens with that. So I have negative 6 minus 3, negative 6 plus 5, 0 minus 3, 0 plus 5, 4 minus 3, 4 plus 5. Okay, let's work those out. I have negative 9 over negative 1, or just 9. Here I have negative 3 over 5. And here I have 1 over 9. Now, all of those, I wanted to deal with this comparison here. Is that less than or equal to 0? 9 less than or equal to 0 is false. Negative 3/5 less than or equal to 0. True. Positive 1/9, positive anything less than or equal to 0 is false. So the only thing that I get here is this region in the middle. So what I have is negative 5, comma 3. Okay, now at the end here we got to be careful because the problem tells us to use brackets. However, remember that denominator equaling 0, that's something we can never hold. We can never have that happen. So this value was a key value, but it was a value that we excluded. So what I'm going to do is I'm going to follow this and use a bracket, but only use it on values that do not come from the denominator. If there's a number that comes from the denominator, then I always use parentheses no matter what the problem says. Okay, so again, if that key value came from the denominator, I always use a parenthesis no matter what this says. Okay, so I have a lot of students, I have that and they're like, oh, I got to remember that, I got to remember that. And they start freaking out and stressing out about that little detail. However, what I want you to focus on right now is getting to the negative 5 and the 3. Doing all this other stuff. This will come. Okay, this is important. I'm not saying that, oh, forget those symbols at the end. Okay, but don't stress out about this because then you lose all of this. When I have a student struggling on this topic, it's not because they constantly make that mistake. It's because they're messing something up here. So again, focus on this general process. These little details will come, okay? I want you to get those down. They're important details. But don't forget about all this, okay? Let's do one more, finish this up. Okay. Big difference on this one, as you can see, we don't have a 0 on one side. We need to make that happen. Okay? So, what I'm going to do is I'm going to subtract this 2. But be careful. You can't just combine a couple numbers here. What we have is 3 over x minus 2 minus 2 less than 0. Now, this is going back to subtracting rational functions or rational expressions. So what we're going to do here is think of this as 2 over 1, and then we need to multiply by that common denominator, or make the common denominator match, and we got x minus 2 on top and bottom. Again, we're not clearing the denominator here, we're making the match. So what we get is 3 over x minus 2 minus, actually I'll put a plus and put the minus on the 2. So we've got negative 2x plus 4 over x minus 2. Okay? These denominators match, so now I can pull all of this together. 3 plus 4 is 7 minus 2x over x minus 2 less than 0. I see some people wanting to multiply both sides by x minus 2. The problem with that is we don't know what x is. And if we multiply both sides by a negative, this has to flip. We don't know what this expression is. It positive, is it negative? So doing that is kind of dangerous because we don't know how that relationship's going to end up. So that's why we need to leave it like this and then we need to go through that table process that we've been doing. So in this case, I'm going to set that numerator and denominator equal to 0. Let me come up here. So 7 minus 2x equals 0, and x minus 2 equals 0. I subtract the 7, and then divide by negative 2. Okay, and then here I simply add the 2, and we got that. Okay, so I create my number line. Remember, 7 over 2 is perfectly fine. I would leave that, but know what that means. 7 over 2 is a 3.5. So I'm going to put 2 here, and then 7 over 2 here. If you want, put a 3.5 there just so you can remember what the true value of that number is. And now, I create my table. Three key values. I'm going to go with 0. Here, between a 2 and a 3.5, I'm going to go with a 3. Sometimes you have to use a fraction. If you do, then you just got to do it. If, let's say, the key value is 1 and 2, I would probably go with 1.5. Okay, but if you can use an integer, use the integer. And then right after 3.5, I would go with 4. Okay, now again, where do we plug in? You can plug in, I would say, here, or you could go all the way back to here. This requires a little less calculation. The problem with it is you have to then compare your number, which might be a fraction, to a 2. So not only do we have to worry about the sign, but we also have to worry about the value of the number itself. If we go here, yes, there's a little bit more calculation, but all we really care about is the sign, because we want to know when that is negative. Okay, so doing it here is probably a little less work, but just be aware that you got to be careful with the comparison. Okay, really look at the numbers. I'm going to go with this. So I've got 7 minus 2 times 0 over 0 minus 2. 7 minus 2 times 3 over 3 minus 2. 7 minus 2 times 4 over 4 minus 2. Okay, I'm going to work from there. 7 minus 0, 7. 0 minus 2 is negative 2. 7 minus 6 is 1. 3 minus 2 is 1. 7 minus 8 is negative 1. 4 minus 2 is 2. So I want to see when these are less than 0. Negative 7 halves. Negative anything less than 0? Yeah, that's true. Positive 1 less than 0? No. Negative 1/2 less than 0? Yes. And there we have it. So what we have is true, false, true. So we go negative infinity to 2, and then 7 halves to infinity. If you put a 3.5 there, that's fine. But if you have a fraction here that's like a 1/3, don't put 0.3, because then that's no longer accurate. Parentheses always on infinity, and since this originally just was looking for less than, there's no brackets involved, I don't worry about where the numbers came from. I just put parentheses everywhere. If, for instance, we started with this, nothing would change except that. That would be the only difference in the problem if we had that or equal to start. Otherwise, again, if there's no or equal to, don't even think about where they're coming from, just put parentheses everywhere. Okay? So as you can see, guys, this is a tedious process. We have to solve. We have to set it on a number line. You have to do this table, but we're not doing anything crazy. The solving, this was probably the most difficult algebra we had to do in this whole section. Okay, but that's nothing new from that's old from chapter 7. After that, we just set these two very simple expressions equal to 0. Very simple equation solving. And this is very simple arithmetic. There's just a lot of it. Okay, the more you have, the more likelihood, the more possibility you have for a mistake. Statistically, it's safer to be flying than driving a car. You can't tell me that it's safer to be thousands of feet in the air than on the ground. However, statistically it is, because there's fewer planes. There's fewer drivers up in the air than there are on the ground. So there's more opportunity for accidents. Same thing here, okay? So don't think that this is some weird, obscure thing. These are very simple steps. There's just a lot of them. Okay, so take your time, be organized, and you'll do fine. Okay? So work hard. Let me know if you have any questions, and I'll see you next time.